this workshop, which is not only extremely stimulating, it's kind of awe-inspiring as well, because you stand here and as Sarah mentioned, you've got Isaac Newton sort of looking at you askance, kind of daring you to do anything wrong. But furthermore, not only are you giving a talk to an eminent audience, you've got Polya and Dirac and Littlewood and Hardy and Landau and all those guys, including my personal hero, Maryam Mirzakhani, the first ever woman Fields medalist, looking at you on the back. So anyway, thanks for that. Okay, now Claudia, you mentioned that there is a football field number of co-authors here. Yes, my talk, similar to a number of other talks that have been given, spans over a bunch of years. So this is a topic that we have been preoccupied with. And I will start from earlier versions of the talk rather than saying, as you recall from last lecture, like another renowned mathematician, Norbert Wiener, used to do. He would come to class after a whole summer and he'd say, so you remember from last lecture. Anyway, so I'll go through that, but hopefully there's something new for everyone. Okay, so let's get started. Here's a little outline. I'm going to tell you, remind those of you who've seen it, of what this stochastic programming optimal power flow model and motivation is. I'll tell you a little bit about the initial pricing and payments that we came up coupled with this auction. I will then present a variation of this pricing and its properties, tell you a little bit about risk. I'll present some numerical results. I will go back to risk a little bit and present yet another pricing scheme, and we can discuss on what I need to go away and do next. Okay, so usually what I do if I'm talking to an audience who is not as learned as yourselves, I start by talking about what an optimal power flow problem is. I don't need to do that now. I just want to remind you that as an auction mechanism, it is an efficient mechanism. It is revenue adequate, and it is cost recovering, something that Ben was calling incentive compatible. This is, of course, when it's convex, right? Okay. So, moving on from our deterministic optimal power flow problems, the premise that this essentially sets this talk and started all of this work was two specific conditions here. One of them was this growing need for flexibility, okay? And hence, I guess, the word flexi-grid in the title of my talk. And then the fact that short notice deviations from pre-dispatch have costs. Now, in the past, when I've been talking about the growing need for flexibility, I'd put up this duck chart. And I was thinking about doing it, and I thought, oh, maybe this is a dead duck. I shouldn't just beat it up anymore. After all, it goes to 2015. And then last week, Anna, who works in control systems, put up the duck chart. So I was invigorated by that. But not only that, last week I was reading the Energy Institute at Haas's blog, and Severin Borenstein was blogging about going to visit the CAISO grid control room. And not only did he have this cool picture, but he also had another duck, right? So this is very much a fresh duck, and it is very much in the limelight. It goes back to February 7th, 2019, and Bushnell and Novan have in fact written about this and have expanded it and noted that when there's a lot of sun, the prices go down, but then when the sun sets, the prices actually climb up quite a bit compared to even prior the utilization of solar PVs, okay, or at least extended penetration of them. So the point I like to make is, unlike, so I'm just trying to see, sorry. Oh, there's the point, right. So unlike what this picture specifically shows, where you're looking at a particular day or an average day, these hills and valleys are stochastic and they move, okay? So the problem is in fact a little bit worse than this. You've got these strains on the network, but you don't know when they're going to occur either, okay? So high levels of uncertainty, the forecast of the pre-dispatch is likely to be, to make it inefficient. We then would have to go forward to real time, and we would have to make expensive real-time adjustments to meet the variations for the forecast. And Victor Zavala and company, who've also been interested in this problem, state that this attribute here can lead to price distortions that can in fact lead to sort of systematic arbitrage opportunities in the market, okay? So put all these elements over there and think about it from the perspective of a bunch of people who've done a whole lot of stochastic programming in the past, and we start thinking, well, maybe what we should do is we should think about a distribution of the outcomes that are going to happen, okay, and make our decisions for what we're doing based on what we may be seeing in the future as well, okay? So that's where our approach was to this, okay? And we decided that we really needed to have a market in regulation or flexibility that they would, that then we would be able to tie into the electricity market, the energy market, okay? So essentially, in the first stage, you are making decisions on where your generators must be thinking about putting their set points, what they can be anticipating to be generating around. And then once you move on to real time, you may have to make adjustments, but hopefully they wouldn't be too enormous in their magnitude, okay? Given that you've considered the distribution. Okay. So, we can think about this as a kind of a day ahead real time, or if you're thinking about it in terms of New Zealand, it would be pre-gate closure and then post-gate closure. So there are a number of periods there that elapse before something actually eventuates, okay? So this mechanism would then allow the participants to price their flexibility coming in, okay? So in a way, we're opening up the market for the participants to say, okay, if the wind is blowing, what I can do is I can go down in terms of how much my set point of generation has been, or on the other side, in terms of demand response, I may be able to rethink the kind of scheduling of the operations that I have had and know that that would come at an expense. Maybe I would have to produce more and store it. Maybe in order to produce more, I would need to have some folk stay longer, and I would have to pay them overtime. But it is an amount of cost, deviation cost, that is something that I know and I can give to the system operator beforehand. Okay. So we've got a tranche T, and it's got an associated ask or bid price, okay? But further to this, we would allow for selling back additional power to the system at essentially a markup, okay? So that's this RT. And similarly, you can ramp down, and although you don't have to generate and you don't incur the cost of generation, the system would end up paying you some kind of a penalty for having to come down. Okay? So what does this look like in the world of stochastic programming? So this is the first emergence of this particular problem, and it's a two-stage problem. So like a bunch of other people here, I am only doing a one-step look ahead, so I'm looking at a static model. So what the ISO is doing is it's solving an optimal power flow problem, but it's in fact doing it over two different time periods, right? So we're trying to minimize the cost of what we are essentially warning the generators to be sitting at in terms of generation, plus any expected cost of deviation that these guys would have. And I want to meet the demand. Not only do I want to meet the demand in real time, I kind of making a plan for meeting the demand in the day ahead or the pre-dispatch period as well. And we've got some prices coming out of these two constraints here, which we will use, which we did use in 2010 for a payment mechanism, okay? So essentially, those first stage prices, we were thinking about them as what it would cost to have the demand go up essentially deterministically 1 unit across the scenarios, okay? And that's what we would pay the generators for the pre-dispatch. Any deviation from this amount of pre-dispatch, then we would pay the second stage price on, okay? So that was the initial sort of payment mechanism coupled with this stochastic program. That's where the prices came out of. And it had this property that it would have revenue adequacy, meaning what you were collecting from the demand and paying out to the generators, but only in expectation, okay? So it was not the case in every scenario. Later on, we actually went back and we had a look at this, studied it, and we worked out that it was cost recovering in expectation as well. And I'll come back to this and I'll talk about it a little bit. Okay, so there may be a deficit in any individual trading period for the ISO, okay? So here's the sort of next phoenix rising from the ashes of the previous stochastic program. We went through, this is with Mette and Endre Bjørndal, and we were thinking, well, is there really any reason whatsoever for imposing the kind of constraint in terms of meeting the demand that we had imposed in the pre-dispatch stage, okay? In the pre-dispatch stage, everything is hypothetical. Why on earth do you want to constrain yourself and ensure that your demand is met? Okay, so we dropped that set of constraints that basically got rid of any of these transmissions, transmission flows that we would have had for the kind of pre-dispatch stage. And along with that, went away this little x and basically said, look, all I have to do is I have to make sure that in real time, in the particular scenarios that I have, I can meet the demand. Okay? The only thing is, now I got rid of my pi 1s because I don't have that constraint anymore, and I've got a bunch of second stage, essentially real-time prices. So what do I do in terms of a payment mechanism? So the answer turned out to be pretty simple, really. Well, actually, maybe not, but we'll revisit that. We said, okay, what we can do is we can just compensate the generator for exactly what they've generated at the realized price, okay? Now, does this have any nice attributes? Well, the nice attribute here that you would get over and above the previous version of the stochastic program is that you now have revenue adequacy in every scenario. And it's easy to see that, okay? Because in every scenario, you essentially have a real-time problem, which is the OPF tailored to that particular scenario, and it would be revenue adequate. This scheme is also cost recovering in expectation, okay, but not in every scenario. And there is a little intuition here that basically shows you, on the other hand, if the marginal tranche has been adjusted downward, okay, so this is the key thing over here, right? So you've got yourself a marginal tranche production and it's been adjusted downward, then this is your realized price, okay? And because it is your marginal cost minus this penalty or this cost of deviation that the unit would charge for ramping down, that unit may be left out of pocket, okay? So in order to see this in a slightly different way, have a look at the following little lemma. It's derived from the Lagrangians, and it tells you the relationship between the real-time production of a particular tranche and what the realized price is turning out to be. And out of this, you can work out what the supplier margin is, okay? And for the generators, on those scenarios where your marginal tranche has ramped down, the marginal tranche will be making a negative amount. Okay? So this is the intuition behind not being cost recovery in every single scenario. Okay, not every tranche is cost recovering in every scenario. All right. The one thing I do want to mention here before I go away is that this set of pricing and dispatch matched with those prices is reversed if you have a flexible demand participating in this market. Okay? So the condition is slightly different for demand, and that becomes a bit important a little bit later on in the slides. Okay. There is a nice little property here attached to the pre-dispatch. The pre-dispatch turns out to be much like a news vendor problem, a quantile of these particular R's that I had. My apologies, I'd called these R plus and R minus before. Those are the same things as RU and RV. Just think about U as op. So the optimal amount of positioning the generator turns out to be a quantile of these realized dispatches, and that particular quantile is a ratio between the flexibility penalties. Okay. Now, we also had a proof here that said competitive equilibrium is equivalent to system optimization, and I'd like to dedicate this slide to Stan, who's a fan of Lagrangians. So this falls out from the Lagrangian of the problem. You just take these meeting the demand constraints, stick them up into the Lagrangian, rearrange the terms, and essentially end up cooking something which is very standard. Yes?
I'm sorry for interrupting.
Not at all.
I'm sure that's a minus, RT minus, or is it a plus? Because if you have minus, it's non-convex.
It's a plus, you're right. Yeah. Sorry about that.
Okay,
yes.
Better.
Yeah, it has to be a plus.
Yeah, it shows up in several places.
Okay, really?
Yeah.
Okay.
After the beginning, it's a minus, RT minus.
Okay, I'll have to go back and I'll have to clean up all of that. Sorry about that.
Yeah, okay,
yes.
Good. Thank you.
Yes. And I thought I'd done such a great job. I spent hours cleaning these up. Still not good enough. All right, sorry.
Yeah, okay, thank you. Okay. Sorry for the interruption.
No, not at all. Thank you for the point. Okay. Okay, so notwithstanding the minus over there, which is it's actually a plus. So what the system is doing here is it's paying whether the generator has to ramp down, we have to pay them. Whether they ramp up, we also have to pay them. Okay. So we stick the Lagrangian up into the objective. And now this offers a way of decomposing the problem across the different agents, okay? Much the same as what every one of you guys, Eve, Danny, Andy, Michael, all of those guys do. And we get a MOPIC out of this, right? And what it shows is exactly the property that I stated up here, that the competitive equilibrium, along with these Walrasian prices that are announced to the different agents, would be equivalent to a system optimization problem. Okay, now the thing to notice here, just before I go on, is that when you decompose this into agents, and you're looking at it from the perspective of each of the different agents, those agents are considering an expectation here, right? Okay? So we have this compatibility between the competitive equilibrium and the system optimization so long as your participants are risk neutral, okay? What happens if we bring in risk aversion into the equation? Well, one answer to this is following Danny and Eve's work and essentially saying, right, we can complete the market. We would then have the right probabilities emerging, And we're back to essentially exactly the same kind of optimization problem that we were looking at, an expected optimization problem over expectation. However, the probabilities have come out of risk aversion of the various agents. Okay? We're interested, however, in looking at what practical instruments one would be able to construct in order to complete the market, as Danny said, because complete markets are utopias. Okay? So for that reason, for the reason that markets are not entirely complete, it probably warrants investigating and seeing whether there is enough of an empirical reason to believe that risk aversion here would be a concern. So if you were going to lose hundreds of thousands of dollars per day, then maybe this would be a problem. If you weren't, then perhaps it's not really such a problem. So that's a numerical study that we undertook, and I'm about to tell you how that went, except I want to tie up two quick loose ends. One of those is that we do have expected revenue adequacy with sample distribution. So Jalal here was talking about not necessarily getting the distributions right when you're addressing stochastic programming and perhaps having small samples. That is a standard difficulty that is raised anytime you talk about stochastic programming. So what we're looking at over here is saying, okay, can we get it approximately right, and would sample average approximation come to our rescue? And the answer is yes, it does. If you do have a continuous distribution and you have convergence in distribution of these approximate samples that you've got and you're solving your problem, then you do get asymptotic revenue adequacy in expectation. Okay? The next thing was another question that said, would your SPOPF perform okay under market power? And this is a track of work that we did with Jawad Khazai and Shmuel Oren back in the day. So it's some time ago, although the paper just came out in 2017, that basically established with a whole lot of stylization, because really what you're doing here, if you're solving if you're looking at a market with exercise of market power, you are looking at these bi-level problems that Sonia was talking about, except the lower level is a stochastic program now, right? So it's even more horrendous. And you're trying to construct an equilibrium. So EPEX, where each of the MPEX is over a stochastic programming problem. So we had to make a number of simplifications here, got rid of any kind of transmission network. We're talking about n-symmetric firms. We confined them to have linear supply functions and, in fact, linear deviation costs, and we made that symmetry assumption. And under these simplifying assumptions, what we managed to find was that the social welfare in the SPOPF was always greater than that of what we call the two-period model, which is the standard exercise that happens in New Zealand, where people lock in their supply functions now. Okay, the market clears based on these, and then you move on to after gate closure in real time, and the same set of supply functions are utilized here. So that brought about some interesting discussion as well, which was related to what was going on in the community at the time in terms of whether or not you should make auction mechanisms kind of more complex by giving people more parameters to bid in, okay? Or should you make it simpler, because then you can look at it and it's more transparent. In this particular case, we found that in the stylized examples, when you had n-symmetric firms, as n went to infinity, people were actually reflecting their true costs and true costs of deviation. And it was not the case for the two-period mechanism. So although we had made the complexity of giving people one more parameter or two more parameters to bid in right, more, that was utilized because they were in fact able to communicate that deviation difficulty to the system rather than having to bury it all into this one supply function that they would put in. So again, a bit of a difference between Australia and New Zealand market versus the US market, where the unit commitment is captured explicitly, but we have to kind of figure it out into the bids that we put in. Okay, so now coming into the implementation methodology, we wanted to have a look at how effective our stochastic program was. So in order to do this, we chose the New Zealand system, which is based on this vast load of information that the Electricity Authority actually has publicized and is available. Every one of you can go and access it as well, including our particular dispatch, which is the VSPD problem. We needed to work out what these deviation costs were for the generators. So we used a proxy for this. The proxy was essentially inverse the ramp rate of each of the stations, right? But we had to scale it in order to get some meaningful numbers. We looked at wind distribution based on 2011 to 2013 data, okay? And then used the distributions that we got over here in the implementation of the stochastic programming model for 2014-2015, okay? The way we did this was we would set up a two-stage stochastic program for periods 1 and 5, which was 2 hours later, so this is after the gate closure, with a sample distribution for wind in the second stage and solve it. So this sample did not come from the 2014-2015 data, but it was out of sample. Okay? We extracted a stochastic programming policy and ran that for period 1, encountering then the actual scenarios. We did the same thing with some kind of an expectation policy, where it's exactly the same problem as up here, except the wind scenario that you're going to see is an expected wind scenario in the second stage. Okay? And we report on these. Now, how did we capture the wind distribution? In order to utilize wind distribution, we resorted to essentially quantile regression methods. My friend and co-author Jeff Pritchard here is a whiz with many things, but in particular quantile regression for wind and also inflows he's been looking at lately, distributions of inflows. Essentially what this came down to was going through, I'll show you some pictures, so this is the best picture here. You look at the current wind, and depending on what quantile you're in, you're going to see a potentially different distribution. So here at 25th percentile, this is the distribution that you're going to observe, say, in half an hour's time. But that distribution changes if you're here in the 75th percentile, okay? So this is the stuff that we had extracted from 2011 to 2013, and we were implementing for the data. Okay. Bulk of the wind is in the North Island and in Wellington. We looked at the particular wind farms that were available, and we had 2 lots, I think. I'm just trying to see. Yeah, so we had those that were conglomerated in the central North Island, those that were in Wellington, and we essentially figured out that they were uncorrelated to one another. So we had spatial correlation of 0. So going through, having implemented the stochastic program for those years, this is the kind of result that we were seeing. So this is January 1st to 31st of December 2014. And what you see is if you took a single period, right, so you made your market settlements period by period, then the kind of shortfall that you would be facing in total across the generators, across all the periods in the year, is somewhere between 10,000 to 15,000, depending on the scale that you're looking at your deviation costs. Okay? So this is really not very much when you're talking about the whole of the electricity market, which is having a turnover of hundreds of millions to $1 billion or more. There are more statistics over there in terms of the number of generators who are making the loss, periods, etc. The one kind of nifty observation here is that you could aggregate paying these generators over a day, so 48 periods, and then the total shortfall basically became negligible, right? So a couple of $100. And it was essentially the same story here for 2015. Numbers look pretty similar, a little bit less than 2014, in fact. Okay? So looking at those particular numbers, I would argue that there wasn't really reason, at least empirically, for any generator to invoke concerns about being out of pocket in any of those particular periods. Okay? But what if we really were worried about risk aversion? Okay? Or if you want to think about it the other way, what if somebody was essentially putting up risk aversion as a straw man, in the place of trying to exercise market power? Then what might happen? So you can go through this, and there's, in fact, it's a proposition, but I guess I just couldn't get it right there, so that's why I called it a theorem. That you can prove that says, okay, if you fix the real-time dispatches, xi's of omega, and instead of your players being risk neutral, you now switch them to being risk averse, okay, then these guys will opt out and they would go for a lower pre-commitment level, so that's that little x, okay, compared to the risk neutral version. And the effect of this decrease in the pre-commitment is that it would increase their expected revenue, okay? So this is essentially a kind of a sensitivity. It's saying fix these guys and you will see a reduction, but you can do the following thought experiment. You can think about a symmetric duopoly when you've got the two generators there and they're kind of signaling that they're really risk averse in terms of having to ramp down and making a negative revenue. And they do this so much so that essentially they price themselves out of having any kind of flexibility in terms of ramping down, okay? Then what's going to happen, of course, is that the system will dispatch them for the minimum and in every scenario ramp them up, right? So in the equilibrium here, the pre-commitment is going to be less than the risk neutral case, and their expected revenue will have increased. So how do you curb that? I mean, it may be that this is not particularly applicable to the paradigm of doing stochastic programming from one half-hour period to another half-hour period, but if we were entertaining thoughts of possibly taking a model like this and thinking about capacity investment, then the numbers could change quite significantly, and this could become a real worry. Okay, so how do you deal with this? Well, the one thing that we hadn't figured into in that little stylized example is that there is this demand response, right? And if those guys weren't flexible about ramping down, well, demand actually does have an incentive to ramp up, so they would produce more and they would collect essentially for the flexibility of being able to produce more for those particular periods when the wind is blowing. So this is coming back to Dick's observation that essentially demand response is quite essential. It basically pops up here as well in this particular auction mechanism. So that's one observation. The second observation is that it is possible to cook up a different pricing mechanism here. So what you do now is in your stochastic programming formulation, which is very much the same as the one that you've seen previously, you have these non-anticipation constraints here, okay? And you dualize these, you take some information or some prices out of these, and you make compensation to the generator based on the prices that you would see over here. Now, this, of course, presupposes that you would compute this particular problem and you would extract the non-anticipativity or the price of information, so to speak, type prices out of this and average them and be able to pay in the different scenarios. Okay, that's one thing. The second thing, this is a very nice attribute of this particular pricing mechanism, is that now we do have cost recovery in every single scenario, so your generators are not able to stand up and say, look, I'm really concerned about being out of pocket. However, implementationally, this pricing mechanism means that sometimes you do, as a generator, actually have to pay back to the system, okay? Otherwise, you would compromise expected revenue adequacy, okay? And the thing, however, that we end up paying here and has been compromised at the expense of having cost recovery in every scenario is that we no longer have revenue adequacy in every scenario, okay? And that's a similar type of attribute to what has been put out by Myerson and Satterthwaite a long time ago, okay? With that in mind, I too would like to wish you all a very happy Nowruz, and as Jalal beat me to it, you can collect your AD from him on the way out.
So Jalal will be your nemesis.
Yep. It's funny, in 2013, in a general meeting in San Francisco, after my talk, I was a PhD student at that time, Ishmael Oren asked me a question about cost recovery and revenue adequacy. I had no idea. And after the talk, Golbon explained me what they are. And now I have to ask questions. Thank you, by the way. So, if I understood correctly, in the early modeling, in stochastic market clearing, we have cost recovery, revenue adequacy, and expectation.
Yes.
Then you remove the day-ahead power balance equality,
Yep.
some variables. So then the problem is less constraint.
Yes.
Then we have revenue adequacy per scenario,
Yes.
while still cost recovery per in expectation.
Yes.
Of course, the system cost should be lower because the system is less restricted, right?
Yeah.
So does it mean that by this way, the market operator shifts the kind of having the risk of missing money from herself to the generators?
Well, no.
Because so now the system cost is lower, very good. The market operator is happy because under any scenario, it's on the budget balance or have extra money. But still, the generators, they are cost recovery and expectation.
Mm-hmm. Yeah.
So maybe compared to the previous case.
No, that's not the case. So I can show you why it's not the case. So the reason it's not the case is that the set of payments that you would give in this third payment mechanism.
Not here, the one
Yeah,
that you
just
have.
hang on a minute.
Yeah.
So in this third payment mechanism, okay, in expectation, these are exactly the same as what you would pay in the second one. The expectation attached to this term is 0, okay? And this is cost recovering in every scenario. The other one is not. It is cost recovering in expectation. This is revenue adequate in expectation. The other one is fully revenue adequate in every scenario. So I think the difference between the very first one and the second one is not so much in the optimization problem, but it's in the pricing scheme. I think the pricing scheme was just lacking something.
Okay.
Yeah.
And the last thing. So
Yes.
in one model, we have one property
Going back.
expectation, the other one per scenario. In other one, the last one that we explained, we have cost recovery per scenario, but we may not have revenue adequacy per scenario.
Yes.
So it means that we can't have all together, but maybe if we have both together, then we are missing the market efficiency. Am I right?
Yes, well, you have a paper on that with with yet another way of sort of running an auction, and you're quite right. You could do that. I mean, the short answer to this, and the answer that I was initially thinking about here, was in these periods when people are missing their money, when you have a total shortfall, just charge from the demand and pay them, right? Sure, that would be revenue adequate and cost recovery in every scenario. But then exactly, but then efficiency is compromised.
Thank you so much.
Sure.
Any other questions? Gotcha.
So could you flip the slide where you mentioned about quantile regression?
Sure. Yep.
So I'm trying to understand where and
There.
how. Okay, so there was a previous one too.
That one?
No.
That
yeah,
one?
Okay.
Yep.
Okay, so the quantile regression is done. Okay, so I think that is there another one before this one?
Yes.
Okay.
By
so
induction, there would be.
So so the quantile regression is used to not really in the model itself, right? It's
No.
actually used to get some data.
That's exactly
Okay,
right. Yes.
Okay. That's okay.
So 2011 to 2013 wind, we
Yeah.
basically took those observations,
Yeah.
looked at them, we constructed these quantile regressions out of them, right?
Okay.
And then we said, okay, this is the kind of distribution we're likely to see.
Yeah.
Go over to 2014, 2015, implement
Okay.
according to these distributions.
I see. Okay. You use those the numbers. Okay.
Yeah.
Okay.
And,
Understood.
and let me just tell you, that just reminds me, sorry, I'll finish off in 30 seconds. In the VSPD, which is the replica of our dispatch problem, it's really quite detailed. What we're doing here is we're coping with reserve requirements as well as all sorts of sporadic outages. There might be a line outage, whatever. So all the data that we're dealing with is quite detailed and very realistic. And that's in fact the reason why we did this.
So I mean, I don't want to ask too detailed about quantile regression, how that's done, because that by itself is not a easy problem. It's a non-convex problem. Quantile regression problem itself is a non-convex. It's like minimizing VAR.
I guess so, yes.
Yeah, and it's so anyway. So I can so it's not a
Sure. So we would use R packages for that, as opposed to
Okay.
like going through and writing an
I
optimization
see.
problem
Okay, so
ourselves.
you use R. Okay.
Yes.
Okay, that's fine. Yeah. Okay.
Okay, we are done with time. Thank you, Golbon. We'll move on.